To start off this demo, I'm going to give a quick overview of our Verilog top wrapper, and then we'll look a little bit more in depth on each of the modules. And to start off, I'll look at these port declarations for the inputs and outputs of the Fpga. We have VGA controls for the display output, and we have an ADC. We have a microphone with an ADC that we've connected to the PMOD connector on the board, and we're taking the clock from the board as well. And the switches are used for controls for the video display. But going through just briefly on all of these modules we have set up, there's a clock generator, which is an IP core, which takes the 100 megahertz clock from the board, and it gives us a 104 megahertz clock, a 65 megahertz clock, and a 16 megahertz. And these go to other modules in our design. One of them being the VGA, which takes a 100 megahertz, a 104 megahertz clock, and syncs that to it's synchronized to a 65 megahertz for the display. And we use a 16 megahertz clock for the ADC, and the ADC module just receives the data from the ADC, which is already in the digital format, but we need to create this serial interface to receive the data. And by running a clock at 16 megahertz, we get a 1 megasample per second rate. And our ADC gives us our input from the mic, and that then gets decimated, and the decimated data goes to our Fourier transform. But before doing the Fourier transform, we have a buffer. We're using BRAM on the FPGA, which is internal memory, and that allows us to store the values from the decimator before we do the transform. And the transform is an IP core, which is integrated in a block diagram. And sticking to the top level here, we have the RAM for not only for the input to the FFT, but we have RAM for the VGA output. So after the Fourier transform is computed, then we store the results, the bins in RAM. And then from that, we can create a continuous output on the VGA. And this module here is which is what reads the samples from the block RAM, which go into the FFT. And the output of our FFT, we actually take the magnitude, and we're only considering the real component of the transform. And so this gives us our output, and it also computes the magnitude. Then for the display, we only consider the first half of this the first half of the index of the frequency bins, and we display that first half on the VGA. We have a VGA, in addition to the VGA controller, we have a plot generator, which generates a histogram where the bar's height represents the amplitude, and the horizontal axis, each bar represents a range of frequencies, which are evenly distributed. And of course, we have another component of our VGA output. So to go into a little bit more depth on the flow of data throughout our system, Peter's going to talk about the ADC and the FFT and what that's all about.
So essentially, the ADC is a board with a serial peripheral interface that we are providing with a 16 megahertz clock. And because each cycle takes each sample rather takes 16 cycles, that gives us a sample rate of 1 megasample per second, as Nick mentioned. And basically the first 4 cycles are leading zeros, and the following 12 are the data bits. And if we take a look at that module, we can see how that's implemented, which Anthony will talk about. But those values are then passed on to the decimator. And this is basically just a way of downsampling in the actual hardware. So rather than sampling at a slower rate from the microphone, we are throwing out every either 32 or 64 or however many samples we want to do, and that will reduce the overall bandwidth of the actual FFT output. So if we sampled at 1 megahertz, that would not give us much resolution in the audio range, but by downsampling with the decimator, we're able to cover a majority and a little bit past the audio range, which is around 0 to 22 kilohertz.
Yeah, and I just want to point out that's what's helping us display a continuous spectrum on the VGA output. With the decimator, we can display the range of frequencies from all the way from the left of the screen to the right of the screen.
And we also have the VGA. We have a VGA controller, which generates timings for the horizontal and vertical position of the currently displayed pixel, as well as a blocking indication when it's not displaying, and a horizontal and vertical sync that are passed on to the actual VGA monitor. And
so I think we're gonna talk about the ADC now, right? Are we gonna
Sure.
open up the ADC? Can you open up the file? Yes.
Sure.
All right. So, the ADC. So this module, what it does, it's not really the analog to digital converter. It represents the SPI interface from the PMOD mic to the board, and basically, if you go through the code, we have as inputs, we have the 16 megahertz clock, as we talked about. We have the reset button. We have outputs. So the outputs are the ADC clock and ADC chip select. They're ready register. And we also have, as the input, we have the ADC SD, which stands for serial data. And that is basically the data coming from the outputted by the PMOD mic, and our output register would be the data, and that would be basically the data outputted that corresponds to what's been recorded on the mic.
Yeah, so if we just take a look real quick, we have the clock and then a chip select pin, which is high when the module would like to request a sample from the microphone. And then at each clock cycle, there's a counter that starts at 0 and will increment through 4 of the leading zeros and then the 12 remaining data bits. And that gives us a 12-bit sample that can then be output on the data register. And then we want to look at the decimator real quick.
Okay.
Yeah, so basically the decimator takes 12 bits, the 12 bits input data in from the ADC's output. And every time the ADC outputs the data, the chip enabled, the input CE, it goes high and increments the 4-bit register count by 1. And when count is equal to 32, the decimator outputs the data to the next module. So the decimator outputs each 30-second data input it gets. And the output new sample plays the role of the chip enable, but for the next module, which is the FFT.
All right, yeah. So those are the most interesting modules we have in our design here, and we've got it all integrated together. And next, after this video, we'll follow up with a live demonstration of the whole system working. I'm going to give a quick demonstration of a Fourier transform on an Fpga. First, I'll show our setup. It's a Nexus A7, and connected to it we have this external microphone and ADC module. Now this provides, via serial connection, the data that is the input to the FFT which is the Fourier transform. And the Fourier transform does the operation and outputs a representation of the result on this VGA cable, and that's what you see connected to the TV. And to test this and demonstrate it, I'm using this online tone generator on my laptop. And to start out, we can use a 5,000 hertz signal. Now that's about 5,000 hertz, and it's a sine wave. As you can see, when I play the signal, and in between talking, you can see on the TV that there's a dominant frequency here, and the harmonics are displayed as well due to the digital nature of the signal processing. But what's interesting is as I adjust the frequency, the display gets updated in real time. You can see that as I adjust the frequency, the horizontal representation of the frequency on the TV is shifting to the left and right with respect to a lower or a higher frequency. In addition to that, we can also demonstrate the volume of the input signal, which is given by the height of these bars. So as I lower the volume, you'll see the bars drop away. And as I increase the volume, you'll see them come back and grow. There's just one more thing I want to show, and that's when we reach the frequencies that become difficult to hear. At this point, you shouldn't be able to hear these frequencies, at least not easily, and you can see that the microphone can still pick them up and the Fourier transform is still computed, and we can still receive a visual representation of the signal.
So this is a MATLAB code that will record whatever's from my microphone, and it will output the magnitude of the Fourier transform of this audio signal. And this is the purpose of this is to compare with what we have from our Fpga. And I'm gonna play a 500 hertz sine wave from my phone, and it should output its Fourier transform. And let's see what happens. So I'm gonna play it and then run the program. Okay, so we have some noise here, but basically we have this one peak at 0.2 radians per second, and that will represent the main sine wave, the fundamental frequency of the sine wave. And these are just, I think these are either harmonics or just noise. So I think they're just noise. And yeah.